So the perceptron model we discussed in the last lecture, and there are a lot of interesting aspects of this. It's well grounded in theory. Of course, we are not going to cover most of this. If you're interested in like the theoretical aspect of this, I will refer you to this book. The other interesting aspect of perceptron is the perceptron can actually represent a NAND circuit. If you remember like what a NAND circuit is from your electronics or maybe some electronics courses, right? You might have seen this. And you know that NAND is like something which you can use to compose like any binary function, right? Which means that if you can build a NAND circuit out of a perceptron, then you can build any binary function using your perceptron, which is quite interesting. Okay. So ideally, not just binary function, if you have a lot of parameters, sufficient amount of parameters, your neural networks can actually approximate any function you write, you can represent that as a neural network. So that's the power of neural networks. Now, this neural network, it's not something new. The earliest one was proposed in, I think, 1957. And this is like the hardware for that. And I think it's very complicated hardware. You can see like, I think there were, these I think are the, yeah, it's providing the power, I think. But yeah, you should, I think, look at this one called like Mark 1 perceptron. At that time, it was very, there were a lot of arguments about this. And ideally, I mean, they just created like 20 cross 20 image. I mean, if you think about this, it just has like 400 pixels, right? So it's a very small image, but still like it required that big hardware, right? So all these wires are kind of, I think, the activations to simulate like the input to the network. So that's what it looked like back then in 1957. Since then, like a lot of improvements have been made, and these days, I mean, you can create your neural networks with billions of parameters, right? So as I said, like a single layer network, yeah, so this is also interesting. We are talking about like adding multiple layers to your neural network, right? But theoretically, you can just have a single layer network, just one layer. And if you have enough parameters, which means like if you have a lot of parameters or many neurons in that layer, you can approximate like any function. Okay? The only issue is like it will require a lot of parameters, and we don't want that. And the reason is that's like one of the reasons we want to go deeper. And again, if you're going deep, we are having like multiple layers. Of course, we can approximate any function we want, and we'll also optimize in terms of number of neurons we require. So the idea is if you have like multiple layers, you can actually treat that as like composition, and you can reuse those compositions, right? So for example, if you have like a layer or a set of layers which are trying to learn some kind of functionality, and it could be like that functionality is required like multiple times when you're trying to approximate a function. So you can reuse that. Okay. So if you're creating a deeper network, it's allowing you to like to use that compositionality, and it's kind of reducing that redundancy when you have just a single layer network. Okay. So that's good. So you might have heard of like MLP. It's just like a neural network with several layers stacked on top of each other. And after each layer, you will have these nonlinear activation functions. Okay, so to each of these outputs, you will apply these activation functions. So this kind of structure is called a multi-layer perceptron, and you will use this term like multiple times in the course. And this is also called a feed-forward network. And sometimes you will see, I mean, even like people use a term neural network for this, which is also fine. Okay, so with this, like the goal is we want to approximate like complex functions, and the kind of architecture which you develop, that will depend upon the problem you're trying to solve. If your problem is very trivial, then you don't want to build like a very big neural network, right? Or a very big MLP. You might consider like few neurons, very small set of layers. So it depends like what kind of problem you are dealing with. That will lead to like the design choices you will use for constructing your neural networks. Okay. Now, before before talking about like how to train these neural networks or like the next topic, I will show you like some results of these MLPs on a standard benchmark data set. So this data set is called MNIST, and this data set has like binary digits, grayscale images, something like this. Okay, so you have 10 different digits. So it has like a lot of different variations of these digits, and they are roughly I think 60K training samples, and you have around 10,000 testing samples, and these are very small images, 28 cross 28. So if you build like a very simple 6-layer multi-layer perceptron, which we described like earlier, then if you use like these many neurons, first layer has around 2,500 neurons, then this next one 2,000, 1,500, 1,500, and then 10 neurons at the end because you have 10 different classes. So this is like the final layer. Then using this kind of structure actually performs really well, and you can achieve a performance of 99% on this data set. Okay, I mean, this is not a very complex data set. It's a simple one, but still, this level of performance actually is pretty good. So that's the power of neural network. And if you think about this, you have like a total of 10,000 total testing samples, right? And an accuracy of 99.65 means you are only missing around like 35 samples, right? So you are making wrong predictions only on 35 samples out of these 10,000 samples, which is quite impressive.